Okay. All right. So now let's share. Okay, you have it there. So let me draw this now. So you have it there now. You have the origin point P is there. So I am saying that would have moved X, then Y like that. Okay, and then let me correct this. Say something like this to this point, then something to this point, and then from this point I go this way. Do you see it now? From the origin. So in this direction and then in this direction. So this is a point in space, and its coordinate is X, Y, Z, like that. Okay. All right. Now, if it had been on a plane surface, we would need only two, X, Y, or Y, Z, as the case may be. So when we are locating a point in space using the Cartesian coordinate system, we need three coordinates to locate the point. But if we are locating a point on the plane surface, like the plane of a paper, or the surface of a room, or the surface of a wall, okay, we need only two. That's, we call it plane surface, the plane surface, okay? All right? So this is what all of this is about. But now, for you to be able to locate the point in space, it means that we need this system, this coordinate system, okay, fixed to a certain object, or to a certain point in space, like the corner of your room that we've just talked about, which you have used to locate the position of this fan, as I'm trying to show here. So now this set of coordinate axes that forms this your Cartesian system that allows you to be able to locate, or if you like, measure the position of the fan, is called the reference frame, the frame of reference, or the reference frame. Let me write that. Frame of reference. All right, frame of reference or reference frame is a set of coordinate axes attached to an object, and that allows us to be able to locate the position of some other object or point in space. That's what we mean by reference frame. Now, that is the whole concept of space that we expect you to know, how to locate the position in. Do you understand that? So, but now there is something else that you has been raised there, which we have also brought in. And I think the reason is that we expect that those that will be studying physics are in this class. So now suppose that I am inside a train that is moving. I'm inside a train. So that's a train. So I'm inside a train like that. So I'm the passenger in the train. Then there is a police officer standing somewhere here. And then I am moving to the right like that in the positive x-axis, as the case may be, right? So this is my positive x-axis like that. Now, if I look out from this train and see this officer, I see him as moving to the left with the same velocity with which I'm traveling to the right. Is that correct? I will see him moving to the left. Is that correct? Yes or no?
Yes, sir.
Yes, sir.
Now, some of you, you see, I will block some of you out of this system. Somebody is wearing a mask in my class. I will record. Good thing that is recorded. I will display so that the VC will see it. Some of you are just loafers. Outright, I think I'm sorry I have to use that. You are loafing. If you are coming to study, you can't do that. You see, this is an abuse of the social media space. You are wearing a mask and you are putting it in the class. It's despicable. Are you alone in this class? I think I've noted the name. I will actually write a report on you and I will post it to the university website or send it to the VC. You think we are coming here to play? This is a class, and you are not the only one. Some people outside this country are attending this class from wherever they are. Now, Wale official, I'm going to, how do I, please come and help me block this fellow. Come and help me block. This is rubbish now. No, I don't want to see this. Who is Wale Official? What's your correct name? You think we are coming here to play? I'm recording this and you cannot do this.
Sir, this is not a mark.
Please block this for me.
Is emoji about the color?
I'm not showing the mark.
It's a profile picture.
It's just
no, it's not. You are not supposed to parade all those things. I don't want to see them.
Sir, you can change it. You can still change it.
Why is he not changing?
Why is he not changing it? What's the meaning of this? You think I'm joking here?
I'm on it now. I want to change it now.
Sir, give him some time.
That's the right name I want to see. I don't want to see all these things.
Picture be that thing now.
Just give him some time. Let him change it. He wasn't aware of it.
While you can go log out, use another email to log in. Then you change your profile picture later.
Use another email to log into this meeting. Put your name there. This is a class. I want to know who I'm talking to. This is a class. Or if you think you are comfortable with this, at least I've facilitated more than 8 classes. I can stop. Don't get me angry, and I will just stop. I'll finish with you if you don't know.
Sorry, sir. Sorry, sir.
Thank you, sir. I'm sorry about it. You see, I don't like this kind of people coming to the class to think that maybe we are playing. We are not playing. This is an official class. It's an university system for your information. If you want people to take your degree, the degree that you'll be parading seriously, this is what they'll be looking at. And you see people who want to see this. Is it clear? So when you are here, you behave yourself well. When I come here, I dress well. You understand? Have you ever seen me, except I'm in my house teaching you? But if I'm in this class, I'll dress well. It's an official class. Now let's get back to what we're sharing. So you can see, I was trying to explain something that I expect you to know about what has been drawn here. Now, this kind of question, this question is not as straightforward as what I'm trying to teach now. Because you will notice that when I was drawing this, I was saying X here, then Y here, and then Z here. But if I had done like this one now, I'm putting Z axis in the horizontal and the X axis here, that's coming out of the board, and the Y axis vertical. It can be anywhere, we can label it anywhere. So that's why I want to spend some time to show you exactly what it is all about, so that if you see any question that we have already asked, you'll be able to answer. So then, what we are trying to say is this. I was trying to show you that somebody is sitting in a moving train. So that's the person. That's the passenger sitting there in a train. And then this is a police officer at the control post. So that's the police officer. All right. And then this is a passenger. All right. Now the train is moving to the right, positive x-axis. Now he sees this person as moving this way, even though this man is stationary. We relate, with respect to the earth surface. All right. With respect to the earth surface. All right. This police officer is stationary. But that is not what this passenger is seeing. What this passenger is seeing is this police officer moving in the opposite direction with the same velocity of this, train. So suppose I ask you a question like this. A passenger in a moving train sees a police officer at the control post who is in motion between the two. Who is in motion?
The passenger.
Between the two. Answer that question. Huh?
The train.
No, I'm talking about the passenger seeing themselves. The passenger is in a train. The train is in motion. We have been told in the question. Is in a moving train. So who is in motion?
The
so
passenger.
I can give you an option. You see now, the police officer is in motion. The passenger is in motion. None of them is in motion also. And I will give you conditions. Or both of them are in motion. You see now, you are saying, So who is in motion?
The police officer.
The police officer.
The police officer is stationary relative to the surface of the earth. But he is being seen as being in motion. The police officer is in motion. Relative to who? Relative to the passenger. relative to
the passenger.
The
The
passenger of
passenger
the
in the
train.
train.
very well then. Then relative to the police officer, is the passenger at rest?
No, the passenger is in motion.
So how would you answer the question now?
Passenger is at rest.
The passenger is in motion
The passenger
relative
is
Okay.
to the
sitting.
police.
Now,
The passenger
no,
is sitting,
no,
so he's
you
at
have
rest.
already said that the passenger is in motion with the train. And you
Yes.
also said the police officer is in motion relative to the passenger. So it means both of them are in motion relative to one another. So if I'm
Okay.
given that option, that's the one you should choose. Do you now see it? The same thing that has been taught, but how to use it in an examination question. Can you see the difference? All right. Both of them are in motion with respect to each other or
Each
relative
other.
to another. Is it clear now? Because relative to the passenger, the police officer is in motion in the opposite direction. Relative to the police officer, the passenger is also in motion. Okay, so here is what this kind of a question teaches. It shows that you cannot describe the motion of anybody or any object until you have chosen the frame of reference. So in the frame of reference of the passenger, which is the moving train, that's a frame of reference attached to the moving train, the police officer is in motion. Okay?
Yes.
And in the frame of reference of the police officer attached to the ground, which is apparently not apparently stationary, okay, the passenger is also in motion. But now, suppose I have said that, okay, there is a stand-up by somewhere there, some other person that is observing these two motions, okay? So this is passenger, the passenger, this is the police officer, and this is an observer, all right? Relative to this observer, this police officer is at rest, is stationary, because he too is stationary. Relative to this man that is also standing somewhere else and is seeing this police officer is stationary. But relative to this man also, this one is in motion to the right, like that. So therefore, for you to describe the motion of an object, you first of all have to choose the frame of reference. Okay, so that is the kind of question. Now, let us also look at another thing. Now, suppose that, I hope you have understood what I've explained so far on that.
Yes, sir.
Is it clear now? Yes.
Yes,
So
sir.
it's simple. In case you see that in your TMA, because I don't know what you were given. This is the approach. That's the approach that I want you to apply. Okay. All right. Now the frame of reference, like I told you, is simply a coordinate system attached to an object or to a point in space relative to which measurements are made, measurements of position, measurement of time, and so on and so forth. Okay. Now, so you understand that now. Now, let me also talk about something else. Suppose that, you see, I have two axes here, two systems here. One is S and the other one is S prime. Can you see it?
Yes, sir.
Yes, sir.
Now, the S prime, let us take this S prime to be the train. So if the passenger that is in the train is sitting somewhere here, and let us call that passenger O prime. That is, he is sitting at the origin of the coordinate system in the train, in the moving train. So let us have this to be that attached to that of the police officer that is stationary relative to the surface of the earth. Do you understand it now? Okay, now the train is moving to the right with constant velocity v. Okay, but now both of them see the explosion of a banger. What do you call it? Knockout or what? What should I use there?
Knockout.
Yes. Yeah. Yeah. Yes. The thing explodes somewhere here, like that. Okay. All right. So, and then they are trying to measure the position of this. So you see that this man that is stationary, that is in this frame of reference here, will be measuring and be giving his own in terms of x axis, x, y, and z, while this one will be giving his own in terms of x prime, y prime, z prime. Is that correct?
Yes, sir.
Yes. So the observer O gives his observation as x prime, y prime, z prime. The observer O gives its own as x, y, z. Now the question is there any relationship between these two coordinate systems? Now, all these readings that they have taken, are they related? In what way are they related? This is what this diagram is trying to show. So now let me answer this question. Let us try to answer this question. I'm going to guide you to answer the question by yourselves. So this is what I want you to do now. Let us see. First of all, notice that by the time my S prime frame has moved, okay, and traveled the distance, because you know that the distance S that is has traveled is going to be equal to velocity times time. That's why I'm putting it here, VT. Can you see it now? So it is at the time when this object has moved this distance that they are making the measurement. Now notice also that my z-axis, z prime axis and z axis and c prime axis are collinear. That's they lie on the same straight line. All right. This is z and this is my z prime, like that. Have you noticed it? Even though I've drawn it this way, I'm expecting that most of them, both of them lie on the same straight line. So they're said to be collinear. Is it clear there? They're said to be collinear. I hope I'm not using terms that are too strong for anybody to follow. Okay.
No, sorry, I understand.
You follow? Yeah. So they are collinear. All right. So now, and then the question is, what is the relationship? What is the relationship between the readings there? So let us read them out. To answer this question, notice that the motion is along the z-axis, the common z-axis, isn't it? So the only one that needs modification is the one that is in the z-axis. The ones that are perpendicular will not be affected because my x and the y-axis are perpendicular to this axis along which motion is taking place. That is along this. This is where the motion is taking place. So this axis y and this z-axis, all right, are not affected by the motion. Do you understand that? Is it clear? So the transformation that we are going to carry out is only going to affect the z-axis. So with that at the back of your mind, choose the correct option here. It says, suppose the origins O prime, and the axis of the coordinates of the initial frames of reference S and S prime in relative motion at constant velocity V along the Z direction are coincident at an initial time T naught. Here is what it means. It means at T equal to 0, these points O prime and O are at the same point. All right, the observers O and O prime are at the same point at T equal to 0. But at the later time T, of course, O prime would have moved away from O, isn't it? So that's what is being asked there. So the question now is, write down the transformation of the position at T with coordinates as shown in the figure. All right. So you choose which one correctly gives the relationship now. Okay. You can see that I've given the correct answer there myself, isn't it? The correct answer is that the transformation. Let me show you. The correct answer is that since this is going to the right and this one is appearing to go to the left, then I should have that Z prime would be equal to Z minus BT. Is that correct there? Now, if these were traveling to the left, if this my Z prime were traveling to the left, then I should have written that Z prime is equal to Z plus VT if it is traveling to the left. Is it clear there? That's
No, sir. Please come again.
That we note the direct response. So I can now complete the list. X prime is equal to X, Y prime is equal to Y, and Z prime is equal to Z. Z prime is equal to Z minus BT. So this is the correct set. All right. So that is what was expected. If you see any other question, the very first thing to check is where is motion taking place? Which direction is the motion occurring? So it is that one that you will transform. All the other ones that are perpendicular will remain invariant. They will remain invariant that's the term, they will remain invariant. Invariant. I don't have space to write that. Let me remove that. Just take note from the word vary, invariant. Does that make sense to you? What I hope you understand what I've just done now. So that answers that question.
Sir, please come again, sir.
You know, we have to hasten up now. We have to hasten up. I'm trying to bring to you some of the things that you must have seen. All right. Okay, so that's number one. Don't expect me to keep repeating myself. I think I've done this enough for you to be able to see. Now, question number two. Apply the method of dimensional analysis to determine the indices A, B, and C in the formula. All right. Yeah. Have you seen this kind of a question? Where C is a dimensionless constant, U is the speed of sound in a gas at pressure P, density rho, and volume V. So the density V is the velocity or speed, C is a constant, P is pressure, V is volume. Hello?
Yes, sir.
Yes. Yes. I want somebody to do that. Do it now. Have seen it? Have you not seen a question like this before?
Somewhat, no, sir.
No, sir. No.
No, sir.
You didn't see it. Suppose I didn't think like that. How would you do it? This is dimensional analysis that I was talking about. Try it out. Okay, now let me show you how to do it. Who can answer that question? So now let me share a Zoom board with you. You can copy the question now. Copy the question. In the next class, I will run one full past question so that you'll be able to follow what I'm trying to do. First, now I want to finish this one. I will do it up to number 10. I'm just using this to teach you so that you'll be seeing the kind of things that we have asked before. Okay, now let me use a Zoom board. You can see here is a question. The question says that you have U is equal to this is capital C, this is P, A, rho, B, V raised to power C, like that. Okay. So the question is that we should find A, B, and C. Small c. Now maybe I don't let us change this one to K. Let's change this to K. Change this one to K. All right. So let's call this K. All right, like that. Now here is what is being asked. The dimensions. Now you know by definition, velocity or speed is equal to distance, which is L over the time T, isn't it? Exactly. So the dimensions of U, now put it in square brackets like that, will be L T, let me write that properly, L T the minus 1. All right, so that will be the dimensions of this. Is that correct? Is that correct? Why? Because this is T to the minus 1. That is, if we carry this up, it will become minus 1. Do you understand it there?
Yes, sir.
Exactly.
Yes.
All right.
Yes, sir.
Then how about pressure? The dimensions of pressure. The dimensions of pressure will be what? How do you define pressure? Pressure is what? Force over the area. Is that correct?
Yes, sir.
So force itself is what? Mass times acceleration, isn't it?
Correct, sir.
Then what would be the dimensions of force? I mean, of acceleration.
Meter per second square.
That's not of acceleration. It's not meters per second. What are the dimensions, for goodness sake? What's the dimension? What are the
Second square.
The units,
Meter per second.
meters per second squared. So the dimensions of force should be what? Mass, isn't it?
Mass.
All right. Then times the acceleration, you said acceleration should be t to the minus 2, isn't it?
Yes, sir.
I don't have where to write that. So this is how I will write it. So this is going to give me over the area. So that means I should have, let me do that analysis before I now bring it in here. You have to know all these things. You see, you have force over area as being pressure, but this is going to be mass times acceleration all over the area. So if this is the area, the length is, area is going to be length times breadth, which is L squared, isn't it? So let me say this side is L and this side is L. So the area will be L squared. Is that correct there? All right. So therefore I can ab initio write this as L squared. But we know that this is going to be capital M representing the dimensions of mass. And then the dimensions of acceleration is going to be LT to the minus 2. You should have seen this from your school certificate. So therefore, what I'm going to have is L to the minus 2 all over L squared. So that means this is going to give me M L to the minus 1 because my minus 2 will go up. All right. I'll have 1 minus 2, which will give me ML to the minus 1, T to the minus 2, all right, as representing the dimensions of pressure. True or false? Is it clear now?
It is.
Yes, very clear.
It's clear. It's clear. All right. So you take note of that. So we have that now. So we have gotten that the dimension of pressure is going to be equal to ML to the minus 1, T to the minus 2. So I can now write that there. Okay. So let me, for want of space, write that here. I can remove that, can remove this, and then I will write it well. You have understood this now. It's unfortunate. These are some of the things that we would have done one by one, but we don't have time enough. I'm trying to do it to give you confidence on this one. So it should be pressure is force over area. So I'm saying it's supposed to be M L to the minus 1, T to the minus 2, like that. Okay. What else do we have? We have density, rho. So you are looking for density. Now, density you already know is going to be mass over the volume. Is that correct? Mass over the volume. Is that correct? Mass over volume. That's
Yes,
density.
sir.
Yes.
All right. It is known. So if you know that, then mass is M already. The dimensions of mass is M. Now the dimension of volume is going to be L cube, isn't it? Is that not true? L cube. That's length times length times length. That's length times breadth times height. So each, whether it is breadth or height, is also a length of a kind. So that's why we are saying length cube or L cube. So therefore, the dimensions of of density is going to be M L. It's not writing well. Let me write this well. M L to the minus 3. All right, like that. So now that's what we are going to substitute in that formula there. Have you written up to this point? So you now have it. You have your U. Your U is LT to the minus 1. LT to the minus 1. Write that well. Then your P as what? M L minus 1 T to the minus 2. And then you have your rho as ML to the minus 3, isn't it? All right. So now, let us remove all of this and have space to write the next stage. Let me remove all this. So we now want to substitute. Please mute yourselves. Mute yourselves absolutely. I'm not going to mute you so that if you are answering questions, you will be able to answer. I will not need to go to unmute anybody. So go ahead and listen, but mute yourselves. Okay, now look at it. So now this constant is dimensionless. This constant is dimensionless. It cannot be determined by dimensional analysis, but only through an experiment. Okay? Now, this analysis is done for the purpose of finding out some certain things, relationship about the speed of sound, because you are being told this is volume. Don't forget, this is the speed. Okay? This is pressure. This is density. So we are being told that the velocity of sound in A depends on the air pressure or the density of the air or the volume. All right? And then we want to find out the correct relationship using a mathematical or dimensional analysis, not through experiments. Okay? So that way we'll be able to find the relationship before we go ahead and go to the lab and find out what this my K should represent. Are you following it now? So now you know that this my K is dimensionless. Let me write there. K is dimensionless. I'm using my hand, so that's why it's dimensionless. All right? Dimensionless. Okay? That's it does not have any units. That's what we are told. Or it does not have any dimension. We cannot determine K. It means that we cannot determine K by dimensional analysis. That's what it tells us. All right. So now, but you know that this is velocity. So this means my U should be LT to the minus 1, like that. All raised to power 1, this side, isn't it? Raised to power 1. So K is dimensionless, so we can neglect it. Then we have already written our P. We said our P is ML to the minus 1, T to the minus 2. Then all of that raised to power A. All right. Then the next one is my rho. My rho is mass L to the minus 3, like that. Then times finally, all these times. All right. Then V is L cubed. This one is raised to power B. And this one is L raised to power 3. All right. Raised to power C, like that. Have you gotten to that point with me? Are you there?
Yeah.
Yes, sir.
Very well then. So from this point, all that it takes for us to do is to, if you look at this is going to give M raised to power A, L raised to power minus A. That's when we multiply this and this. All right. When we multiply A and minus 1, we give minus A. A times minus 2 here, T to the minus 2 will give T to the minus 2A. All right. To the minus 2A. Like that. I don't have enough space. This cannot be ruled. How do I do it? Let me check. This is my whiteboard. Unfortunately, it's not like I'm not using the type that I can just rule with my hand and it goes up. I cannot do it like this. Let me see. What is this? I'm trying to look for more space. All right. But don't worry, right as I go, then we can carry all of this. Then the next thing is, we are finished with that. The next one is ML to the minus 3. So this is going to give M raised to power B, L raised to power minus 3B. Then finally, we have L raised to power 3C. All right? So we multiply that. So look at it. So this is the first one. So if we multiply all of these, I'm going to have M raised to power A. Of course, you know, when we have the same basis, we add the indices. Is that correct? So this is going to give me M. Where do I write this now? Have you written up to that point? Can I clean up the top?
Yes, you can clean up, sir.
I can clean the top up.
Yes.
All right. So I can remove this now. Can remove this. I will still leave the first part there. I'm going to remove this now. So you write as I go. Please, if you have any question about the what I'm writing, you let me know, because the thing is somehow not writing smoothly as I expect. Okay, so you now have m. So this gives us m a raised to power m raised to power a plus b. When the bases are the same, you add the indices from your secondary school elementary algebra. M a plus b, all right, plus b. Okay, then we take L. Then I have L raised to power minus a. I also have L raised to power 3c minus 3b. So that means I'm going to have L raised to power, of course, I'm going to add all of that. So it's going to give me L is equal to, L is L raised to power minus a minus 3b plus 3c. Okay, that's what it should be. Next one, I'm taking T. Now, T is simply T to the minus 2a. We have already obtained that. So we are now going to equate everything there to this other side, which is L T to the minus 1. All right, which is exactly the dimensions of velocity. So we can proceed from that point. So all we need to do now is to equate the indices of the corresponding quantities. Now, for the m, now you notice that this is my left-hand side. So let me write this the way it ought to be. So let me take this to the left-hand side. Where do I move this to? I want to remove this to somewhere else. Does it move? It doesn't.
We can't see it clearly. It is.
You can see now, can you?
Yes.
Yes, I'm trying to look for space. Okay, so I think I have enough space now. So I should have, I'm going to take this now. So it should look like this. I'm supposed to have LT to the minus 1 is equal to everything I've written here. Is equal to this. So write it like that. So it means I'm going to have M A plus B L A minus 3B plus 3C.
Plus A minus A.
Then T to the minus 2A.
I think that's L minus L raised to minus A. Minus
L raised
to minus A.
I'm copying from what I've written.
Yes. L raised to power minus A.
So minus A?
Yes, sir.
Is that what we had?
Yes.
Yes,
Is that what we wrote before?
Yes,
yes, minus A.
Okay, whatever it is. Now, here is what you are now going to do. You see, there's no M here. There's no M on the left side. It means M raised to power 0. M raised to power 0 is equal to 1, isn't it? So it means the whole of this times 1. So that's how we answer A. So it means therefore that, do you understand it now? So that means the index for M on the left-hand side is going to be 0, or the power is going to be 0. Do you understand that argument there?
So how?
Anything raised to power 0 is 1.
Okay.
Your mathematics is not good.
Then 1 minus 1.
No, it's not a laughing matter. You are laughing. Your mathematics is not good. This is elementary. This in your secondary school. Are you not coming from secondary school into this class?
No, I didn't follow you up. I didn't follow what you were saying.
You didn't follow. So I'm coming to teaching this in my class. Yeah.
I'm flowing with you.
No wonder. Now let me tell you why you are having problems. When you see these things, go and try them out. You see, there's nothing we are going to teach here that's going to be built on an assumption that is not going to be built on an assumption of something you have already done. That's how it is. All right. Now, I'm saying that anything raised to power 0 is equal to 1. Correct, is equal to unity. Anything raised to power 0 is unity. There is no power, then there is unity. You see, why there's trouble in Nigeria is that some people are more powerful than the others. If there was no power at all, that is everybody's power neutralizes the other. Then there will be unity.
Yes, sir.
That means we will all be 1. Will you
Yes.
remember it that way? When we
Yes,
raise
sir.
anything to power 0, it is equal to 1.
Yes, sir.
And anything multiplied by 1 is itself, isn't it?
Yes,
Does it
sir.
make sense? So that is
Yes.
why I'm saying, so in order for you to equate the left-hand side to the right-hand side, you have to write m raised to power 0 on this side, like that, isn't it?
Okay, yes, sir. Yes, sir. Makes sense.
So that way, it means that I'm going to equate everything here. 0 is going to be equal to minus a plus b, from which I'm going to get a equal to b. So I have a and b already. Is that correct? A is equal to b.
Yes, sir.
So, but I don't know. We know that a is equal to b, but we do not know what a is going to be. All right? So we can find a from something else. Hello?
You can hear you.
Yeah, somebody else was talking now. That's why I'm stopping.
Okay.
Mute yourselves so that we can do it. Do you understand how we got to this a equal to b now?
Yes, sir.
Exactly. All right. Now, so I can erase this now. Okay, let me erase this. All right. So you know that. So we now have a is equal to b. So we have that. So now we have equated the indices of m. Okay, we have equated the indices of m. Let me rewrite this well. I'm still having this place as L T. So I'm having m raised to power 0 L T to the minus 1. So that's how we got it. So now I have equated this with this. All right. That's how we got a equal to b. All right. Then next we equate that of L. So I'm going to have L, the power of L here is 1, isn't it? The power is 1, isn't it?
Yes, sir.
Yes, sir.
Yeah, that's correct. Okay. So that means we are going to have on the left-hand side 1 is equal to a minus 3b plus 3c. Are you there?
Yes, sir.
Yeah. All right. So it is from this now, we already know that a is equal to b. All right. So but then let us use our t. So right at the next one here, we have t. That's equating that with this one, t to the minus 2. What do we get there? 2c. What did we write there?
2a.
For the last one. Minus 2a. Is that the last one?
Yes, sir.
Yeah, minus 2a. Yeah, so that means we are going to have minus 1 is equal to minus 2a, isn't it? So that means my a is going to be equal to half, isn't it? And that means
Yes,
since a is equal to b, b is also equal to half. All right?
Okay.
Yes.
Yes, sir.
So we have half here. We have half here. Then we can now find what c is, isn't it?
Yes,
Since
sir.
we have, so all you need to do, I'm going to leave you there so that you can solve what is left. So you are going to come here and write, so I'm going now to this other equation that I have b and c, c, all right? To come here and put, is going to give me a is a half, so that's going to give me half, then minus 3 over 2, b, minus 3 over
Times.
2, minus 3 over 2, since b is half, plus 3c. So if we do that, I'm going to have 1. Can I wipe the top now? Can I wipe this off?
Yes, sir.
Just try it out. You can try it out. Is why I made it that way is because it is a TMA question, so that you will teach. It will teach you the principle. All right, you learn the principle. After we finish that, then it is easy for you to apply it to simpler ones in an examination condition. That's how I do my own. Okay. So that's why it is advisable you don't give your TMA to be done by somebody else. Do it by yourself. Or you can do it with people. Or anybody that is doing it with you should teach you exactly what it is. Just like I'm doing now. All right. So then there you have it. So we have that 1 is equal to half. All right. Minus 3 over
Minus
2.
3 over 2.
Yes.
Plus
Plus 3c. All right. So
yes,
this
sir.
is going to give us if we transfer this to the other side, it's going to give us 1.5 plus 1, which is 2.5, then minus half, which is going to give us 2, isn't it? Therefore, my C, all right, is going to be, do you understand what I've done there?
No,
I'm doing
sir.
that one. No, you have to do it mentally. I don't have enough space to write. This down to this other side, isn't it?
Okay.
1 minus half will give you half.
Okay, okay.
Then take this down to the other side, it will give you 1.5. All right. So you add to this 1.5. All right, and a half. That's going to give you 2. Is that correct? So I'm going to have
yes. That's true.
That's correct
true,
now. Yes. So you have 3C is equal to 2. Therefore, my C is going to be equal to 2/3.
2/3. Yes, sir.
So therefore, you now go here and write the correct equation. Does it make sense now? So it's supposed to be something like this. Can I wipe some of these off? Can I wipe this off?
Yes.
Can I wipe this line off? Write it as I'm going. So yes, so then we can write off. We can write this with all the values that we have obtained. So it's supposed to be something like this. It means we are saying that our U is a certain constant K, all right, which we do not know, all right. P raised to power half, rho raised to power half, okay, and a volume V raised to power what? 2/3. So now, of course, this is half. So that means I'm supposed to have K to the square root of P rho, like that, right? Then V. How do we handle that? We can still modify that much further. Okay. Let me give you. The question said we should find what A, B, and C should be. So let us even stop there. Okay. So but then we are going to write. We'll simply introduce these quantities, and then you have the relationship between your U, which is the velocity, the pressure, the density, and the volume. So these are the answers. Whether we have done it correctly or not, that's whether we have gotten the precise answer or whatever. The procedure does not depart from what I have just shown. I hope this is clear now. Do you have any question on that? Is it clear now?
Yes, sir.
It's clear. It's clear. It should be. I expect everybody to know that. Now, be patient. Let me take you through at least 10 questions of these. Okay. After all, I started late to wait for everybody to join. I think the class is becoming larger. It's about 36 now. When we started, it was about 7. Okay. So this is a typical old TMA question that I've done before. Okay. There are so many of them. Okay. That I may not have time to teach, but this kind of deal that I'm doing will allow you to be able to answer the questions. I think that's what we should be. Look at it there. Okay, see, I think that means there's something that one of the indices is not correct because one of them says A is half, B is minus half. So repeat the process using the method I've used. You should have A is equal to half, B is equal to minus half, and C equal to 0. Maybe I will try it out. I will try it out again. Let me see if there is. I will try it out again, and then if anybody tries it out, you must have called out something that a minus sign somewhere because you said the minus that I can't tell whether it was the minus that I wrote earlier on. Okay.
Yes, the M
Yes.
supposed to be raised to power A, but you wrote minus A.
Raised to power A.
You who called out a certain quantity, right? Called out a certain quantity, and I think that's. Then do it again. You are going to get it right. So that is the correct answer. So this is the kind of analysis I expected you to do. Is it clear now? For that question, is it clear the method?
Yes, sir.
Yes, sir.
So you're not sharing your screen, sir.
Those female ones. Okay, sorry. Let me take you back. Can you see it now?
No.
Yeah. Yes, sir. Yes, sir.
That is question MCQ2.
Yes, sir.
Now calculate the direction cosines of A plus B, given that A is equal to 4 I hat, 7 J hat minus 5 K hat, and B is equal to 3 I hat, 4 J hat plus K hat.
K hat.
Now, what do these my I, J, K represent? What, who knows? Hello? What do we mean by A? You know, this is vectors now. Hello? Are you there?
Yes, sir.
So, did you see a question like this?
Yes.
Did you answer it? Did you answer this question by yourselves?
Yes, sir.
Okay, so that means, okay, choose the, right, now solve this problem quickly and give me the answer if you have solved it. Because I'm going to solve it before I show the answer. Okay? Because if I show the answer, everybody will assume he or she knows. And I'm not going to do that. I want us to solve this while we are still here. Now, let me suggest what to do. So, A plus B. Now, A is a vector, B is a vector. That's why you have arrows. Let me explain a few things there. A with an arrow like that shows that it is a vector quantity. So, I, J, and K are unit vectors in the X, Y. Please, that person that is allowing the child to call. Mute yourselves now. Mommy, can I shut the class or are you still there? Can I still continue?
Sir, we are here.
All right. Okay. So you have been given A here. This is A and B. So once we put an arrow like that on top of the a quantity, we mean that it is a vector quantity. All right. Now, written materials, it might be written in bold characters. If it is written in bold character, then it means it is a vector quantity. If you are looking for its magnitude alone, then we can write the module of it or the modulus. This is the same thing as this might be without an arrow. It means I'm referring to only the magnitude. The magnitude. Magnitude means size. Magnitude. All right. Magnitude means size. So if I'm talking about size, I'm not interested in it, and we need not only the size, but we also need the direction. Such quantities are called vector quantities. Vectors that we measure, quantities that we measure without need for specification of direction of measurement is called scalar. Scalar. Guys, we simply need a certain scale, right? A graduated scale of any kind at all, and then we have done the measurement. Is it clear there? Well, that's why it is said to be scalar. That it is based on what your divisions on the scale. Okay?
Yes,
do you understand it now?
Yes,
So
sir.
it's scalar. That's all. It's scalar express the size only. But once we talk about vector, it means we are going to write. We are going to express the magnitude. The quantity. The correct description of the quantity is going to be with two numbers with appropriate units. A vector quantity is suitably described by two quantities. That's two numbers with units. Because what's a quantity? A quantity is simply an expression of an observation, a phenomenon, or anything at all by a number. That means we have measured it. You see, these are the things that I teach in your PHY 101, the mechanics part. Unfortunately, this time around, I had to drop it so that there will be peace. Because people were complaining that I'm teaching what is not in the course material, so I dropped it. But I expected also a communication that will ask them to drop it from their TMA, but it is not. So the next time around, we are trying to produce a book that combines the two sides in one course material without it being too long. So I think that's a challenge that we are having, because those that selected this should have done this, but it wasn't done. So, and it is not my fault. Okay. So, but when I was teaching it, these are the kind of things that the nitty-gritties that I teach first before I now bring them to this kind of scenario. All right. So that's what we mean. The scalar, the vector. So a vector quantity. For instance, if I'm going to say to go to Kano from Abuja, I have to turn north. You see now? So I'm going to say, I'm going to turn 90 degrees towards the north, isn't it? So that's one quantity. That's direction, 90 degrees. So the quantity now is direction. I've given the number. The unit is in degrees. Can you see it now? So that's why I'm saying a number with a suitable unit. Any physical quantity will have the size. The number represents the size, and the unit represents the scale of measurement used. Does it make sense to you? What kind of scale? Now, if I'm measuring direction, I'm not using the meter rule to do it. I'm using a protractor, which measures angles. Okay? Are you still there?
Yes, sir.
So you can see now I am beginning to remind you of the things. I'm reminding you of the things that you have heard. So I'm simply, you cannot tell me you didn't hear it. So now here is the summary of what I'm saying. You are talking about the vector. It means you are going to have magnitude and direction. Magnitude will be represented by one number representing the size and the units. Then direction, another number representing another quantity and units. But when you are talking about the scalar, it's going to be just one. For instance, if I'm saying the mass of a tennis ball, I'm going to say, okay, it is 20 grams. That's the end of it. No direction. But if I'm going to talk about the direction of a force, okay, I'm saying, okay, a tugboat is being pulled by a force of 2,000 newtons above, at an angle of 30 degrees above the horizontal. Can you see now? So it means that for that I have given the magnitude of the force, the direction also. Two numbers. First is 2,000, and then what's the unit? Newtons, and I said it's going to be maybe kilonewtons, okay? Newtons or whatever. Then the other one is direction, measured in what? In degrees. So these are the kind of things that I expect you to have at the back of your mind. Now back to the solution, so that we do not deviate too much. We won't deviate too much from it. So now let us look at it. So when you are writing like this, let me now solve the problem. I'll help you to solve the problem. The starting point is this. The direction cosine, what we mean by direction cosine is this. Where do I put it? Let me put it on the Zoom board so that you can see it clearly. So the direction cosine, all right? So suppose I have the origin like that. That's the point P. Let me draw this well. I'm drawing it from the origin like that. So that's the point P. Okay? So this is the point P here. Now this is the position vector of point P. Now the coordinates of point P, as I've shown you earlier, will be X, Y, and Z like that. I hope you understand that. Okay, yes, so this is my Z direction. Let us take this to be the X direction, and this is the Y direction like that. If I'm doing something like that, then you understand it. Now, so what do you mean by direction cosines? Okay, the angle between this and this, between this, my position vector, and this is angle alpha, okay, is called, this is, we can call this my M, all right? Now, let me not call, use the M. So let that be the angle which the position vector R here makes with the x-axis. That's angle alpha. Now, but this also makes an angle, all right? This is beta, all right? With the Y, that's Y, with the y-axis. That's my position vector also makes an angle with the y-axis. So we call that beta. Then the angle which this my position vector makes with the z-axis, we call that gamma, like that. That's what you see there, because somebody was talking about vectors in 3 dimensions. All right, so that is it. So this is the position P. So what we mean by the direction cosines. So the direction cosines are, so what we are looking for is cosine of alpha, cosine of beta, and cosine of gamma. Those are the direction cosines. The direction of these angles is what we mean by the direction cosines. All right?
Yes, sir.
Did you see the material? PHY 111, if you did the... So, but the most important thing to note here is this. Of course, how do we get the magnitude of the that of my R vector? Of course, the magnitude of my R vector, as this, is going to be equal to the square root of x squared plus y squared plus z squared. Agree?
Okay.
It's not okay. You are saying okay. Are you learning it for the first time? It's not about being okay. Have you seen that before? Do you understand what that means?
Yes, sir. You understand.
Very well then. But you know, of course, let me simply draw your attention to if we are going to talk about in the direction of x. Of course, this direction is going to be if we drop a perpendicular from P to the x-axis. Okay, then I'm going to have a right angled triangle, isn't it? So the square root on the hypotenuse, which is r, okay, is going to be the squares on the other 2 sides, isn't it? You already know that. But that's not what we are looking at. We are looking at the part that gives us the x is the adjacent, not the opposite, isn't it? So the hypotenuse in this case is this. The adjacent is this side, or this one, okay? Now in this one, the adjacent will be this one. Will be this one. The adjacent will also be this one, okay? For the case of this angle and for the case of this angle. So that's exactly what has been done. So in other words, what we are saying is that my direction cosine m, let me now write it, m is going to be my cos alpha, n is going to be cos beta, and sorry, LMN. It's supposed to be like that, in that order. L is going to be cos alpha, M is going to be cos beta, and N is going to be cos gamma. Let me show you this, where it is in your course material, so you can go back and read it. For the benefit of all, look at it here. It was not drawn well there, but I think I have the one that I've done by myself. I have redrawn this. Let me show you. Let me show you where it is before I go on. Okay, it's here. You can see that this is not done the way I wanted. Let me share it with you. Did you see it now? Can you see this one now? Where you read it, it's going to be found on page 1. I think this page it's not numbered. Page 38.
Okay.
Go and look for it there. Okay? But I
Thank
think
you,
you
sir.
have understood what I mean. You can see they have done exactly what I mean. Now, this is my x-axis. Can you see it? This is the x-axis, so that if you are reading it, you understand. This is the x-axis now. So, and this is the position vector. This is the position P. Okay? So the position vector, my R, all right, is inclined at an angle alpha to the x-axis, inclined at an angle beta to the y-axis, and inclined at an angle gamma to the z-axis, which is what I drew earlier on the zoom board. Is it clear now? So you can see what they have done here. It is the same thing that I've said. So it's easy. You can see now how they derived it. All right? So whatever they have said, they are telling you that is cos alpha for x. So y is cos, all right, cos beta, and z is cos gamma. So that's what they intend to write there. It's just that the notations for the people typing this was not quite mastered. So this is supposed to be OP, all right, squared. So now when they do this, this is equal to the square root. Of course, that's what I wrote here, that my R is going to be the square root of x squared plus y squared plus z squared. This is not 2 squared, z squared, z. Are you following? So when you are reading, this is what you get. But you know that sine alpha, cos alpha, that and all of that is going to give us this, all right? And we can show, I have shown it. I think I don't want to waste time. I've shown it somewhere. I've done it. That cos alpha plus cos beta, sorry, cos squared alpha plus cos squared beta plus cos squared gamma will be equal to 1. Can be shown. I've shown it myself. I don't know. I cannot go now to begin to. Let me see. Give me a minute. Let me bring it from my own drawing. Give me a minute. Okay. I think it will pay us if I show you the one I've drawn properly. Give me a minute. I'm going to show you. I hope I can find, because I label my own as units 1, 2, 3. Let me see which one is this. No, let me not share this. Let me open it to the book that I've written on this. Give me a minute. I want to show you the whole thing so that you can get the diagram properly. Give me a minute. I'm still coming. Let me see if I can get course material development. I think there's, yes, I have seen my own book here that I wrote on this. So you are going to see the whole thing. I think it's supposed to be unit 3. Is it unit 3? Unit 3 vectors. Just a minute, I'm going to share it with you. I want to open to the exact page. My own content is much larger than what you have there, in the sense that I draw the diagrams myself, and then I try to, yes, I think I have seen it. Now, very, very soon now, you are going to see the solution. So maybe I shouldn't even write the solution. Let me open it straight to it. Yeah. Let me show you what I've done. All right, gentlemen and ladies, this is what I want us to share. Unit 3. Can you see it? Direction cosines. Are you there? Can you see it?
Yes, sir.
Can you see it?
Yes, sir.
Please, can you see this green page that I'm apparently green page that I'm showing? Can you see it?
I can see it.
Yes. Now, compare it with the one that you have there. You notice that the one that you have seen there, you see that this beta is well drawn. So in this case now, you see this is my, I'm taking my x this way, my y here, and my z, all right? Which is the usual way of doing it. But whichever way, all you have to ensure is that the angle between this your position vector, let me take a pointer, this your position vector. This is the point P, this is the position. So this is the vector from the origin, drawn from the origin to the point P, all right? Now, this vector makes an angle alpha with the x-axis. This is a unit vector in the x-axis, I hat. Then it makes an angle beta, this angle, all right? This angle beta, okay, this was not done. This is beta, okay? This is beta here. That is, this is beta, this is the one. So All right, so you mark that. If it wasn't marked, all right, so that's how it should be. And then this makes an angle of gamma with the z direction. So that is it. So now look at the derivation there. It's quite easy. Look at it there. So consider the position vector of a unit point P, which is OP, that is my R. We can write this as R, that's using the vector notation. Vector notation, we can write it as this. It shows us the direction we have had to go. We have to go my R. I have to go X unit in the X direction. This is a unit vector in the X direction. Then I turn around and move Y unit in the Y direction. And then I turn around and move Z units in the Z direction. All right? So that's what it is. So it means X, Y, and Z, these, and these, are the scalar components of the vector R in the X, Y, and Z direction. That's what it tells us. So I've explained that. X, Y, and Z are scalar components, X, Y, and Z are scalar components of R, okay, in the direction X, Y, and Z. And I, J, and K are unit vectors in the mutually perpendicular directions, that is along X, Y, and Z direction. Now you understand that. Of course, the directions are OX, OY, OZ, like that. Do you understand it now? Then the magnitude of R alone, as I've said earlier on, of course, is going to be, the magnitude alone is going to be the square root of X. This is this quantity. That is R, which is this. We can write it this way, is equal to the square root of X squared plus Y squared plus Z squared, like that. Okay? Do you understand that? So that's how we got that. Now we define the direction cosines as the cosines of the angles which OP, that's my R, makes with the positive X, Y, and Z directions. All right, respectively. I've already explained that. All right. So if you take note of that, then we can write these cosines representing them by L, M, and N, as I did before. You now see it. That's how I got it. Okay. Maybe I shouldn't deface this so that if you are screenshotting it, you can get exactly what I've written there. Okay. So you understand it now. So it's easy. Okay. So that's how we got that. So if I am doing that, it means therefore that I am actually saying that what I'm actually saying is that, of course, I know that my L represents cos alpha, M cos beta, N cos gamma. So if I'm saying X squared, Y squared, Z squared, so I'm saying it's going to be cos squared alpha, then plus cos squared beta plus cos squared gamma. So the next stage that we are going to write is that, just that. Look at it there. So if you take a closer look at that figure, this is my figure. This is my figure. Okay? Take a closer look at it. Now, if you take a closer look at that figure, you agree that these cosines can be written in terms of X, Y, and Z and R as this, isn't it? Of course, I've already told you it should be written as, because I said cos of alpha is going to be the X side over the hypotenuse, which is R, isn't it? This is for alpha. Then for Y is going to be cos beta. The Y side, which is the adjacent side, there over the hypotenuse. Then for gamma, cos gamma, which is going to be the Z, which is the adjacent in that case, over the hypotenuse. The hypotenuse is R. This is not gamma. Let me write it well before we make mistakes. This is R, okay? Or if you like, the vector R the modulus of the vector R, which I said can be written as R. I hope you understand that. So that is where you are. So that is how I wrote all of this. That's how I got all of this. Okay?
Yes, sir.
But then you know that my R, from what we have already seen, that my R is the square root of X squared plus Y squared plus Z squared, isn't it? So it means that I can, instead of R, I can write it this way, isn't it? Like this. Are you following? But you also know, we also said that cos squared alpha, you can prove this. Cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. I don't need to prove that. If you want to prove that, I think I've shown the proof there. Let me show you the proof using the simple definitions that we have used before. Right? All right. So you can see, so I'm saying cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. It means x squared over r, the whole of r is this, from what I've shown here, plus y squared over this plus z squared over this would mean the whole of this is equal to 1. Can you see it becomes easy? Now, the question that I gave you, is it here? Now, look at the example. Look at the example I gave. Look at the example. So with this example, I'm going to leave you to go and solve the other one.
Okay.
Yeah. So with this example, it says if A is equal to this, A is equal to this, B is equal to this, find the direction cosines of A plus B. I could have asked you, find the direction cosine of A, find the direction cosine of B, find the direction cosine of C. Okay, whatever. All right. So but now what we have done is to ask you to find that of A plus B. That means we first start by finding A plus B. So vector A plus B means add the corresponding components. Look at it here. X component added to the X component here. So this is going to be 6 plus 5. Can you see it? Then times I, which is this one. Agreed? Then this one is 9 plus 6 in the y direction. Yeah. Then minus 7 plus 2 in the z direction. So that will give us this. Is it agreed?
Yes, sir.
So it's carefully done there. Then how about the magnitude? The magnitude alone is going to be the square root, as we have said here. That is, we said, let me write that again. You said the magnitude, that is my R, okay? That is that's the magnitude of my A plus B. All right? Is going to be what? The square root of these my quantities now. As this one is 11, so it's going to be 11 squared. This one is 14, isn't it?
Yes.
I hope you are following. How do we get 14? 9 plus 6 is 14. No, it's not 14, it's 15. I hope you are correct there.
It's 15, it's 15, sir.
Yeah, so correct that. Yes, it's 15.
It's 15, sir.
15 squared, so plus that, plus 15 squared. Then the next one is what?
Minus 7 plus 2.
Which is minus 5.
Minus 5, yes, sir.
All right, so if you square that, okay. So I think there was a slip here. So if you do that, this is going to give 121. Then 15 squared is going to give us 200 what?
25.
225, yeah. Correct this. So you do that. Then plus 25, 250 plus 121, add that up. What will it give us?
376.
376, is that correct? 376. So it's going to give us a square root of 376.
Oh, sorry, 386.
386, the square root of 386. 386, like that. Then the next thing is for us to begin to look for how do we group this? Is this number divisible by 3? To know that the number is divisible by 3, add the digits. It gives us a number that is divisible by 3, then it is divisible by 3. So 3 plus 8 is 11.
11.
Plus 6 is 17. It's not divisible by 3.
That's all. Not divisible by anything.
Is it divisible by 7?
No.
How do you know? You look for the last 2 digits of the number. If they form a number, that is divisible by 7, then that number is divisible by 7. You know that? Test for divisibility.
Okay.
Then is this 14. Number divisible by 4?
Please, I not get.
Is it divisible by, I'm asking now, you want to try to take some numbers away from the square root. Is this divisible by 4?
No, it's 96.5. It's not divisible.
It's not divisible by 4.
Yeah, 96.5.
All right. So let me leave it the way it is.
Okay, divisible by 2 though.
No. Look at what I'm trying to look for here. I'm trying to look for a square under it. You know that 4 is a square. 9 is a square. 16 is a square. You know that?
Yes, sir.
Yes, that's what I'm trying to do. 25. Okay. So then I would have further simplified it. But that notwithstanding, we can go ahead. So all we will need to do now is to come now and now that we have this, this is my R, I mean my the modulus, that's my this is supposed to be the vector that I'm dealing with, the magnitude of the vector I'm dealing with. So it means therefore that I'm simply going to have the top is going to give me, this is going to give me 11. So the correct answer in this case is going to be 11 all over the square root of 386 in that case, not like this one that we factored. Okay?
Okay.
That's my L. Yes. Then my LM, then my M is going to be what? It's going to be 15. Is that correct? 15 over 386, the square root of that. And then my the final one,
N.
LMN is going to be what?
Minus
5, isn't it? Yeah. All over the square root of 386. That solves the problem. That's what we mean by the direction cosines of that. Okay, so you can now go back and solve the other one. Does it make sense to you now?
Yes, sir.
Is anybody drowning in that case? Have I drowned anybody?
Yes. Yes.
Is anybody that was drowned?
Yes, me.
You were drowned?
Yes.
The rescue team is here now, so let's hear you. On what? All right. So please follow that example that we have just done, and then try to solve the other one. I don't know if I've even solved it or I've given it to you in this question. I don't know. I mean in this class. Can I answer a question on that briefly before we go? Let me try and make this a long class for the purpose of is this the one that I gave you in the that one? Is this the one?
Yes, sir. Yes, sir. Yes, sir. Exactly.
This is the one I gave you, isn't it? I didn't solve it.
Exactly. Yes,
I have the solution. All right. So that means I'm the one that said this one now. All right. Okay. So. Okay. Can you go? Can you now attempt to solve that on your own if I leave you?
Yes, sir.
Yes, I will solve it. I will solve it and bring the answers back. All right. Okay. Now I think that is that about that. Now let us go back. You go to market. Please mute yourself. Now who is this that's making noise? Oh, today you went. Hey, Lawrence, stop talking to your family in the class. All right, so please try and solve that now. You should be able to have it. Whatever it is, justify your understanding of this. I think this is what we got. I hope it's correct. All right. Do you understand it now? Are you there? Can you see it?
Yes, sir. We can see it, but we have not yet solved it, but we can see it.
Yes, solve it and get back to me.
Okay, all right. Sir.
I want a feedback on that. Now, here is another one. If A is given as this, B is because she said we were given vectors. So I think maybe I should even give you, we don't have any more time. Can I really take a class and give you a talk on vectors as a whole? Then you you'll be satisfied that most of these things can be handled. All right?
Yes, sir.
But now, that's if we can fix a long class. Yes, and then everybody will go and buy data for themselves.
Yes, sir.
Now, so in this one, it says if A is this, vector A is this vector is given as this. Find a unit vector N normal to the plane containing A and B such that A, B, and N. Now, N is a unit vector, right? That is perpendicular to the plane containing A and B. That's what the question is saying. In this order, find if A is this, find unit vector n hat normal to the plane containing A and B such that A, B, and N hat in this order form a right-handed system. So what do you mean by right-handed system? I hope you can now see that we are beginning to bring in the language of physics and mathematics. Okay? A right-handed system. You know what we mean by right-handed system?
Yes, sir.
How many people have seen a screwdriver?
Yes, sir. We've
Yes.
seen a screwdriver before.
Yes, sir.
Yeah. All right. I have drawn it somewhere here. Now let me show you in. It's good that I've opened this my course. Let me show you. I've actually rewritten from this to give to the university part of it. All right. This is my own impression. Some of the things that I've actually taught. Okay, in my own class. Then I've formed them into this. Supposed to be a book. Taking a cue from what we've been doing in class. So but there again, look at it. This is what we mean by right-handed system. Can you see it now? Hello, are you there?
Yes, sir. We can see it, sir.
Yes, I can see it.
Right. Yes.
Right. Screw.
Now, what that tells us is this: if I am rotating, a screwdriver advances in the direction shown. All right. If I am turning it in the counterclockwise direction, if I'm going like this, you can see the direction of my arrow through this angle as I've shown here. Then the thing will advance in this direction here. So if I am rotating A vector A towards the direction of B like this,
Raphael, please turn off your mic. Turn off your mic.
Then this is going to advance in this direction. And I've drawn it here again. This is the direction of somebody turning a screw. So when you turn it this way, the direction of the thumb shows the direction of the advance. This is the direction of the advance of the screw. So this is called the right-handed screw or the right-handed system. The cross product is given by the right-handed system. Now here is what we mean by the cross product. The cross product can be written as A cross B, all right, is represented by this. And we are saying it can be A, B sine theta, all right, this angle theta here. So it's going to be the magnitude of A times the magnitude of B times the angle of, times the sine of the angle between them, which I have shown as theta there, okay? Can anybody mention any specific application of this? You see, we have the dot product A dot B, all right, which is A, B cos theta. The magnitude of A times the magnitude of B times the angle between them. All right. So if I drawn something like this, so I have A. So let me say, let me show this. For instance, I've drawn something like that. Now that represents F, and then this represents the distance it has moved from here to here is S vector, all right? And this force is making an angle theta here. So this represents work. The physical representation of the dot product is work. That's what I want you to see, all right? The dot product has a physical meaning when we are talking about work, the work done. Now work is F S like that, F dot S, where F is the force and S is a displacement. You define work as force times displacement, isn't it? That is force times distance in the direction of the applied force. So that's why I'm writing F dot S, where S represents displacement. Displacement is distance moved, in this case, in the direction of the applied force. Is it there? Do you understand it now? Hello, are you there?
Yes,
People
sir.
of the world, are you there?
Yes, sir.
I have, because I didn't hear the response. Okay, maybe I should shut down. I think we have to fix extra classes for you. How do I do it? I should fix an extra class. All right? Because I want to review this. I want everything to be treated. I don't want anybody to fail and come back. Don't come back. I want you to go forward like that. So this one now represents what we call torque or moment. Moment of a force. All right? Moment of a force is a measure of the rotational effect that the force produces. So if I touch a door by the edge, okay, you will notice that I can set it in rotation about the hinges, isn't it? That's an axis through the hinges. Is that correct?
Yes.
Let me allow you to see my face so that you understand what I'm saying. Can you see me now?
Yes, sir.
Yes, sir. Yes, sir.
Now, this is the door. This is a force. And the door is hinged here. So this is the axis of rotation, the hinges. So the axis will pass through like this. So this is the door. So if I want to open it, I will push it. It can go like this. Open it and close it like this, isn't it? Now, the force that I'm applying, if it is perpendicular to it, it will be most effective, isn't it? Now, notice that the force I'm applying, which is this, all right, is at a distance away, okay, from the turning point, which is this axis, isn't it? So
Yes, sir.
can go in like that or come out like that, isn't it? Are you following? Now, this distance to the point of application of the force is called the moment arm. You remember that? The moment arm. Remember that? So let us call that my R, okay? Moment arm, R, okay? All right. Now, let me show you one thing. If you apply the force at this hinge, that's at my elbow here, will you be able to turn this object into rotation?
No.
Try it out. Can you rotate this, my hand, applying the force at this point?
No, sir.
At this point?
No.
At this point. Of course, it will be very difficult to set it in rotation. You notice that as you go along here, all right, the force becoming more effective, but becoming more effective at this point, isn't it? That's number one.
Sir.
Number two, if I'm applying the force at an angle like this, all right, will it be more effective than if I'd applied it vertically like this? Are you following?
No.
It will not be as effective.
When I am applying it vertically, if I'm applying at an angle, it's not very effective. But if I'm applying it, so it's only a part of the force that is perpendicular that will be effective in rotating these objects. Can you follow?
Yes, sir.
That's true,
Yes.
sir.
So in other words, we are saying that the perpendicular component of the force, okay, is the part that sets up the torque or the moment. Is it clear then? So I have done that. I have drawn some diagrams on that. But let me see. So I think for you to be able to understand this, I have to effectively show you this. So I've asked you a question here. Most common one I expect you to remember is called moment of the force or torque. And I think I've actually drawn the diagram of what I'm trying to explain. This is a door. You can see a door here. Okay. You can see a door. All right. This is the axis through the inches. So if I apply a force like that at the edge, it will be most effective. Now notice that if I resolve these forces, we'll have the horizontal component and the vertical component. The horizontal component has no effect in bringing about rotation because it lies along the direction of application of the force, that lies along the direction here. So therefore, the component of the force that lies along here that passes through the pivot point, okay, does not produce rotation. It's only the part that is perpendicular like this that produces rotation. So that's why we are right. Now that part is, of course, the vertical part is going to be F sine theta, then times the distance, F R sine theta, as the case may be. All right, that becomes the moment. Now, this one, F cos theta times R, F or R cos theta is going to be equal to 0. All right. So the effective part is FR sine theta. And this is in consonance with the definition of the cross product. Don't forget we said that my cross product is supposed to be A cross B. Now in this case, F cross R, where my R is this distance. Do you understand it now? Or if you like D, okay, whatever. Is it clear now? So if I write this as AB sine theta, then I should write this as FR sine theta. Is that correct? So you have seen all of this, And these are some of the things. But what I am effectively saying is that this is called the moment or torque. Like that's the physics term, torque, T-O-R-Q-U-E. All right. Any question on that? Do you have any question on that? So I will leave you to go and solve this because I think we have had too long a class. Let me show you some of the things that we have asked. Displacement of a particle from a reference point at any instant is given by this, where S is in meters. Calculate the average velocity of the particle. Now, before you go on, let me show you what to do in this one. And I've given the correct answers. All right, I've given the correct answers. So what I expect you to do is this. This is what I expect you to do. He said you should find N. So this is so I have a plane. Let me draw it. So you have a plane like this. That is a plane surface. So I have my A here. Sorry, I have my A here. And I have my B here like that. So I'm looking for a perpendicular N. I hope I can draw it well. Yeah, it's there. It should pass through this point. Okay, so this is my N hat. So this is the angle given here, isn't it? So you can find the angle here, isn't it? From what we have done. Okay, you should be able to find the angle between this and this. So you have A and B. Now, these are the X, the Y, the Z, the X, the Y, the Z components. All right. So you are asked to find a unit vector. A unit vector. So what are we going to use in this case? What are we going to use? So if this is my A, and this is my B, okay? All right. And I know that my A cross B, all right, is supposed to be a certain vector C, and that this my vector C is supposed to be perpendicular to the plane containing A and B, and setting up what we have just said, the right-handed system. Do you understand it now? So it should be possible for you to find A cross B if you know what we mean by vector product. So you can find the vector product first. Once you have gotten the vector product, then the next thing is for you to find the unit vector, all right, in the direction of the resultant vector A cross B. That is the answer to that question. And it should be this, my last option. Go and try it out and be sure you have gotten it. If you don't get it, if you don't solve it, so if you are cooperating with me, then I'll bring the solutions. So try it out, and I want somebody to come out and tell me, okay, I've seen it. This is what it is. That I've given you the parameters because I don't have time. All right. So now here is that's number 4. Number 5. Number 5. Let me show you. Are you still there? Are you still there?
Yes, sir.
Yes, sir.
I don't want to do like Pastor Chris Okote. He said, if you are there, say, You know that pastor, that TV pastor? Say, are you still there? If you are there, say, So that you will be sure nobody has slept in his class or in his one is
yes,
teaching. Okay. All right. All right. So you can see. So I will solve this problem when you have tried it out. These are some of them. These are some of the problems that I've given. I'm just choosing this as a guide. I don't know what you have been given, but I began by asking you what you were actually asked. Okay, I think I'll have a class, another class. Can I hold this class now? I asked these people that I want to teach them PHY, classical mechanics. All right, so this is a question. This is another question. You can screenshot this. The displacement of a particle from a reference point at any given instant is given as this. We can't ask you this in the exam. You won't be able to do it, but I'll ask it in the TMA. So if you see a thing like this in the TMA, you should be able to solve it. All right. So what we are actually testing here is called calculate the average velocity. All right?
Okay.
Of the particle in the time interval this and this. And its instantaneous velocity. Average velocity. Now, average velocity is different from instantaneous velocity. The average is total time, total distance over time taken. All right? So for me to find the distance in this case, my S, that means I'm going to have S, this is 3 into 5 squared, all right? Minus 4 into 5 plus 5. Then that's at the final time. Then minus the whole of this, minus 3 into 3 squared, 3 squared, minus 4 into 3 plus 5. So that will give me the distance, isn't it? So that is going to give me 25 times 3, which is 75. Is that correct? Minus 20 plus 5. That will give us what? 75 minus 20 is what? Hello? Wake up now and be in the class.
55, sir.
55.
55.
55. All right. So that means I'm going to have, so this is going to give, please be careful what you are calling out, 55. Then this one is going to give 9 times 3.
9.
Which is what?
27.
Then minus 12 plus 5. 9, that's 27 plus 5, that's 32. Minus 12.
20.
So this is going to give us what? 55 minus 20.
35.
Eh?
35.
35.
Yes, sir.
Be careful. Now, so 35. So that's going to give us 35 all over the time taken. The time taken is 5 minus 3, which is 2. So I do not see your average velocity in that answer. Now, 25. Let me cut it out.
Okay.
25 times 3 is 75. 75. 80. 80 minus 20 is 60. So you called out the wrong thing. It's 20. Myself? Right. 20 divided by 2. 60 divided by 2. Are you following now? This is supposed to be 75. All right? Plus 5, which is 80. 80. Then 80 minus this one, minus 20.
60.
Which is 60. All right. Okay. Then then the time interval is supposed to be what? 5 minus 3. 5 minus 3, which is 2. So it's supposed to be 30 meters per second for the average speed. The instantaneous speed, so that means supposed to be 30. It's not even included here. Do you understand? That is, it's supposed to be average speed, which we have just calculated. This is the distance all over time taken. So the distance that we have taken is 60 meters. Then all over the time taken, 5 minus 3, which is 2. All right. So that will give us 60 divided by 2, which is supposed to be 30. Then for the case of the instantaneous velocity, let me show you what happens. In the case of the instantaneous velocity, it's different. Instantaneous velocity means, you see, it's unfortunate that we haven't had time to teach this. If I want to teach this, it takes an average of over the 8 weeks that you are supposed to do this. All right. Here is what I'm saying. What I'm saying is that this is equal to S for the 5 seconds, all right, minus S for where S is the distance, 3 seconds, all over the 5 seconds minus 3 seconds. This is going to be in meters per second. Do you understand it now? So that's what I've done there. Do you understand that? That's average. The distance moved will be, to find it, what you do is that you substitute 5 for each of these. 5 squared, 25, okay, times 3, 75. Then 5 here, 20, all right, like that. That's how I got all of that. Then divided by the time taken, all right? So that gives you the first part. Does it make sense?
Yes, sir.
So that's the average velocity. Then how about the instantaneous velocity? Instantaneous velocity. V. Okay, so I want to end with what I've just tried to explain. So I hope you understood what I did there. So that means this is supposed to be 30. It's supposed to be 30. All right? While this is supposed to be 20. Yeah, you differentiate this.
So I couldn't get the part of the instantaneous velocity. We did not get that part.
Instantaneous velocity means the limit of the average velocity. All right? Let me write it this way. Change in S in this case, all over the change in time, as the change in time tends towards 0. As the change in time tends to 0. And this can be written as ds by dt. It becomes the first derivative. Is it clear? So that's the key thing there. So that's what we mean by instantaneous velocity at an instant. An instant means that the time is negligibly small as the time tends towards 0. That's what it means. So it becomes the first derivative. Okay? Is it there? Are you there? Do you understand me up to that point?
Yes, sir.
Hello? Yeah.
Yes, sir.
So that is how I got that. I showed you how I got the first part. So if you differentiate, of course, the x, let me write it this way. If I'm given, your mathematics has to be very good. A x raised by n. Is the dean in the office? Dy by the x is going to be equal to n times a, na x raised by n minus 1. So that's what we are going to get. Is that clear? So if you do that to this, it's going to give us 2 times 3t, which is going to give us 6t. Is it clear there? Now the other one is 4t raised to power 1. If you differentiate that, it's going to give us 1 times 4t, all right, raised to power 1 minus 1, which is t raised to power 0, which is equal to 1. So that's why I said that this is, when we differentiate, we are supposed to get d, so I'm supposed to have ds by dt is going to be equal to 6t plus, 6t minus 4. 6t minus 4. Okay? So now, but at t equal to what? At t equal to 4. So when I put t here, all right? So this is going to give me 6t minus 4. So it's going to give me 4 times 6 is 24 minus 4, which is equal to 20. So the first part was this, and the second part is this. So the correct answer should be the one that is written like that. All right? Is it clear to everyone?
Yes,
Hello?
sir.
All right. So those are the things that I have actually asked in some of the emails. They are taken from all those things that you have in that course material. They are there. But the truth is that they were never solved, they will never solve a problem like that or so and make you become familiar with what it means. And what I do is that once I teach, I will try to tell you the physical meaning of what has been written. These are not ordinary mathematical equations. They are telling us about the physical situations, what is happening in reality. Okay, so those are the questions. Now, after this, you will notice that the next set of 5 questions, the way we have asked this, the next set of 5 questions or thereabout is going to come from heat. This is the way I have always arranged. All right, you can see this one now is on thermometry, isn't it? So the next set of 5 questions. Okay, you should be able to solve this. I've solved this in your class. Eh?
Yes, sir.
I can leave you with that. You are quiet. Can you not solve this one?
We can solve
We
it.
can, sir.
Yeah, because I've solved this one. Then the next one, you can see. So because I'm a bit at a loss as to what to do for you, all right? It's difficult. Then this one is about, yes, the figure shows a spectacular scene of part of Victoria Falls. Victoria Falls is found in which country? I think it's in 2 countries in East Africa. Okay, Zambezi, over the Zambezi River in southern part of Africa. I think, is it Zimbabwe and where? The Victoria Falls, that big fall. I think you can find it out on the map there, but I think it's Zimbabwe and I think Kenya also. All right, so this is the world's largest feet of falling water on Zambezi River in the southern Africa. The average height and flow rate of the fall are given as this. All right. If the temperature of water at the top of the fall is 24.5 degrees Celsius, calculate the temperature at the bottom of the fall. Now, the assumption is that all of the potential energy at the height is converted to kinetic energy, all right, and therefore thermal energy. Now, this is what happens. Let me show you. All right, so the water falls, the water comes like that, and then it tumbles. So at this point, this is PE. Of course, it also has kinetic energy here, isn't it? Because the water is moving. All right. Okay. So, but let me make it a bit simpler. That everything here is potential energy. At here you are potential energy, then plus kinetic energy. Okay. At this point now, you have all kinetic energy. All right. But now the kinetic energy here is converted to the thermal energy part of it, isn't it? To thermal energy. So the assumption is if all of these have been converted to thermal energy, all right, so I'm supposed to have mgh is equal to, let me show you. Now mc, all right, delta T, where this is a change in temperature. All right. So if I do away with the m's, then I'm supposed to have that delta T is going to be equal to GH all over C, where C is a specific heat capacity of water. Okay. And this has been given. Okay. Now, for you to be able to solve this kind of problem, you have to be to arm yourself with this kind of information. Now, the question says calculate the temperature, okay, at the bottom. So you should be able to get it. The change, is it the calculate the temperature. So what I've given here is the change in temperature. So the temperature at the bottom can be calculated from that. These are some of the informations that these kind of things is because nobody has come forward. When you were answering your TMA, nobody came forward with anything to ask questions. You don't come through the what do you call it? The discussion forum or anything. If you bring it there, I will be able to answer it. Question number 8. If I should finish this before we go.
There's no way we can draw
a piece of
question there.
metal has a mass of this in A, and this remains. I
said there's no way we can write in the discussion forum except you initiate. We cannot write in the discussion forum except you initiate a conversation there. And we will now begin to reply.
No, you can write in the discussion. You can write it now. In the discussion forum, you can start. In the discussion forum, you type the questions. All of us will be prompted. We'll go there and then we'll go and we'll see it. And then some students will see it. I will see it also. And then when some people have discussed it and suggested solutions, I will also give my own idea. Anyway. So now this one has to do with what? This is what we are told. Let me show you. Go and answer, try and answer it. So this is the object. Yeah. So it is immersed in water. So it will have an upthrust U and the weight down, mg. All right? This is the Archimedes principle or the law of flotation. Is that correct? So we are putting an object there. All right? Suspend. So it will experience an upthrust U and the weight downwards there. So but the principle states that the amount of water that is displaced, that's the water will rise from this up here. The amount of water that is displaced. All right? Is it clear there? Or the amount or the mass of the water displaced. Okay? Or the weight, if you like, of the water displaced. Okay? Is equal to what? Who knows what I'm trying to talk about? You have not read it. It's in your textbook now. We are now talking about Archimedes principle. It's equal to the upthrust. The upthrust is equal to the upthrust. That's the force, the buoyant force that pushes the object upwards there. Okay, that tends to lift it up while it is inside that fluid. Is equal to the mass of the liquid that has been displaced. Now, the mass of the liquid that has been displaced can be calculated from the density that has been given, mass over the volume. Okay, mass over the volume. Okay, that's all you know. So it means therefore the mass that is displaced will be the density times the volume, like that is equal to the mass. Okay, all right. Now, but now you can also talk in terms of the weight, since we have given you that's the weight of the liquid displaced. Okay, will be equal to the upthrust. So that can be calculated from this relationship. Okay? I will solve them and bring them only if you have attempted them. So that is that one there. Finally, you have the last two questions on this. This question number 8, 9, and then 10. That gives 10 questions. I have 1,001 of them here that I have said over the years. Okay, I've said, I think I have 1,000, more than 1,000, 3,000. Questions here, all right, that I have said. Beginning to have an unstable thing. So I think we can, let me just show you the remaining part of the questions without solving them, since we don't have any more time. I have other things to attend to. So when next do you want us to meet? Outside the class, outside the normal class. This one says how much heat is transferred in 1 hour by the process of conduction through a concrete wall whose thickness is given like that and all that. Yeah, I think they do. Can you all hear me?
I can hear you now.
Yes, I can hear you.
Like me, I want to think. And it was very good. I think even though there's no point in thinking of
Class, and
many of us who want this, even my own election.
All right. Okay. Can you hear me now?
We can hear you, sir.
Can you hear me now? Some of you that are talking.
Please
can
mute
you all
yourself.
hear me?
Yes,
All
yes,
right,
we can hear you,
all
sir.
of the class at this point. So what we will do is this. We will reschedule the class.
So you're saying APC in spirit.
Now, what I want you to do is this. Jen.
Yes, sir, I can hear you.
And I have a lot of followers. I can see this. And they love me, and I love them.
Yeah.
Sir?
Who should I hand this over to arrange the next class, an extra class? Jen, can you arrange it, or I hand it over to Raphael?
Raphael, please do so.
Raphael.
sir.
Raphael is not there. Jen, can you arrange for an extra class?
Okay, no problem, sir.
I want you take the responsibility and arrange for an extra class. Give me the time and I will send the text across to everybody.
Okay,
all right, sir.
So with that, good night. Thank you very much for your patience. I have some other duty here.
Thank you, sir.
Thank you, sir. We will do all of these. All right. So good night.